Okay, folks, the goal of the second problem is to derive what we're going to call the characteristic equation or the characteristic polynomial, or sometimes called just the characteristic formula. By the way, this is related to our term, the characteristic equation, that we used when we were talking about the solutions to nth order linear homogeneous ODEs. So there's a similarity in that vocabulary. That's not a coincidence, but we won't see that connection in this first example. So instead, our goal is to derive this formula or derive this equation, which we will be using in order to compute both eigenvalues and then their associated eigenvectors. So I say here that this is something that I'm going to expect you to do on our third exam, the proof of this formula. So let's return to our definition of an eigenvector. Remember that we said that for a linear transformation, we've got T mapping from Rn to Rn. So this is a linear transformation with associated matrix A an eigenvector of T is a vector V satisfying AV equals lambda V. So that's what we meant by an eigenvector. It's one where doing the linear transformation to that vector is the same thing as simply scaling that vector. Okay. So what we'd like to do is have and by the way, we call lambda then, in that case, we would call lambda here an eigenvalue. So we'd like to have a nice way of finding eigenvalues and then their associated eigenvectors. And the way we're going to do that is with this formula right above here. So I'd like to take the definition of what it means to be an eigenvector and derive this characteristic formula. Okay, so how are we going to do that? Well, the first thing, it's kind of a slick trick. On the left-hand side, we've got a matrix times a vector, and on the right-hand side, we've got a scalar times a vector. But to be able to do some matrix algebra with that, I'd sure like to have a matrix on the right-hand side. So what I'm going to do is I'm going to rewrite the right-hand side as lambda I times the vector V, where I is the n by n identity matrix. And then I'm going to go ahead and subtract the term on the right to the left, so we get that matrix A times V minus lambda I times vector V would be equal to 0. Now careful, what object is this 0 over here? This isn't the number 0. Here we've got an n by n matrix times an n by 1 vector, right? And here we've got a scalar times an n by n matrix times n by 1 vector. So what type of object do we have on the left-hand side? We've got an n by 1 vector. And so what 0 do I mean over here? I mean the 0 vector in space. So careful with that. Here I am talking about the 0 vector. So by the distributive property of matrix multiplication, I could go ahead and factor out that eigenvector V there, giving me this expression here. Okay? So now either vector V is identically equal to the 0 vector, which in that case it's technically not an eigenvector, and we're not going to consider that, or this matrix right here is singular. What do we mean by that? Well, remember that in some cases, when I say solve AX equals 0, the only solution to this equation right here is the vector x equals 0. That is the only solution if matrix A is invertible. Why can we see that? Well, if matrix A is invertible, then we could multiply both sides by A inverse on the left, make that a 0 vector, and that would just give me x bar is equal to the 0 vector, and that's the only solution you get. But if matrix A isn't invertible, then this equation could have infinitely many solutions. And if that's the case, then we call it a singular matrix. And what's another way of describing a singular matrix? Well, a singular matrix is one where the determinant is what? Let's be careful here. If I can invert matrix A, then it's a non-singular matrix, and the only solution to this equation is the zero vector. But if I can't invert matrix A, then it's non-singular, or excuse me, then it's singular, and what's its determinant? Its determinant would have to be 0. Matrices that cannot be inverted have a determinant of 0. And there is our characteristic equation that we were wanting to derive. Okay, so I said I was going to ask you guys to do this on a test, so let me just rework through that procedure in a little more streamlined fashion. So we start out with, here's our derivation of the characteristic equation, and we start off with the definition of an eigenvector. Okay, so there's our definition of an eigenvector. To make this easier to work with in terms of matrices, I go ahead and think of it as lambda times I times v. And then I go ahead and subtract everything over to the left-hand side. Now careful here, what 0 is on the right-hand side there, that is the 0 vector. Then I can go ahead and factor out the vector v from this expression, and this has two solutions. This happens in two cases. Either vector v is equal to the 0 vector, which in that case it's technically not a eigenvector, and we don't want to consider that trivial case, or a minus lambda I is singular. What do we mean by saying it's singular? We mean that its determinant, a minus lambda I, is equal to 0. Careful here, folks. This 0 here is the 0 vector. This 0 here is the 0 vector. This number here on the right-hand side is the number 0, the scalar 0 in the real number system. And there we have our derivation of the characteristic equation. Folks, we'll be working with this more and more. We'll get to see why this is a useful equation, but this video was meant to just show you the derivation of the formula.